If 1 upon A, comma 1 upon B, comma 1 upon C are in arithmetic progression, then 1 upon A plus 1 upon B minus 1 upon C into 1 upon B plus 1 upon C minus 1 upon A is equal to. Since A, B, C are in AP, so we have the condition 2 times B is equal to A plus C. So let us here 2 times of 1 upon B is equal to 1 upon A plus 1 upon C. Or we can also write 1 upon B plus 1 upon B is equal to 1 upon A plus 1 upon C. Or we may also write 1 upon B minus 1 upon A is equal to 1 upon C minus 1 upon B. Or we may also consider 1 upon A minus 1 upon B is equal to 1 upon B minus 1 upon C. Depends upon the situation what is required, you may use it. So let us consider 1 upon A plus 1 upon B minus 1 upon C into 1 upon B plus 1 upon C minus 1 upon A. So here in the first case, I can use 1 upon B minus 1 upon C. 1 upon B minus 1 upon C, we can add 1 upon A minus 1 upon B. So we can write here 1 upon A plus 1 upon A minus 1 upon B into, and in the second case, we can write 1 upon B minus 1 upon A. So the second we can consider here 1 upon B minus 1 upon A is equal to 1 upon C minus 1 upon B. So we may consider here 1 upon B minus 1 upon A. We can write it as 1 upon C minus 1 upon B plus 1 upon C. So that is 2 upon A minus 1 upon B into 2 upon C minus 1 upon B. Further simplification, 2 2s are 4 upon AC minus 2 upon BC and minus 2 upon AB plus 1 upon B square. So further simplification, we can write 4 upon AC minus, and even we can consider here minus 2 common, or minus 2 upon B taken common. So we may write 1 upon C plus 1 upon A. So 1 upon C plus 1 upon A from the first case we can write 2 upon B. So we may write here 4 upon AC minus 2 upon B into 1 upon B, and again the remaining case is 1 upon B square. So plus 1 upon B square. So 4 upon AC minus 2 upon B square plus 1 upon B square. So here we can write 4 upon AC and minus 2. So let us check once again, minus of minus plus 1 by B square. So 1 upon A plus 1 upon C is 2 upon B. Sorry, this is 2 upon B. So this is 4 upon B square. So minus 4 plus 1 is minus 3 upon B square. So 4 upon AC minus 3 upon B square, which is our option A. We need to find the value of 3 upon 4 plus 15 upon 16 plus 63 upon 64 and so on up to n terms. So we may write 3 upon 4 as 1 minus 1 upon 4, and 15 upon 16 we can write 1 minus 1 by 16, and 63 upon 64 is 1 minus 1 by 64 and so on up to n terms. So we can take 1 plus 1 plus 1 and so on up to 1 n terms, and again minus taken common 1 by 4. So 1 by 4 plus 1 by 16, that is 4 square, 1 by 64, that is 4 power 3, and so on up to n terms, that is 1 by 4 power n. So here we can add 1 is added n times, so n minus, and here we can use the concept it is a geometric progression whose first term is 1 by 4 and r is equal to 1 by 4. So we may use a into sum to n terms in GP is a into 1 minus r power n divided by 1 minus r. So we can add 1 minus 1 by 4 whole power n divided by 1 minus 1 by 4. So let us write here 1 by 4 into 1 minus 1 by 4 power n, the whole divided by 1 minus 1 by 4 is 3 by 4th. So we may consider, we can write n minus 1 by 4 into 4 by 3 times of 1 minus 1 by 4 power n. So which is n minus 1 by 3 times 1 minus 4 upon n, or we can also write n minus 1 by 3 plus 1 by 3 into 4 power n, or 4 power n we can take to the numerator, 4 power minus n divided by 3. So we can go with an option B. Option B is the answer. We need to find the sum of the series, or let us consider the sum as 1 plus 2 into 2 plus 2 into 2 square, 3 into 2 square plus 4 into 2 power 3, and so on up to 100 into 2 to the power 99. So here 2 is multiplied for each term, and let us multiply with the s. 2 times s is equal to, and let us multiply 2 and to be written the next line, the next step. So let us write 2 into 1 is 2 plus 2 into 2 into 2 is 2 into 2 square plus 2 into 3 into 2 square is 3 into 2 cube plus, and so on we can write. Here we can say this is 99. So 99 into 2 to the power 99, and again here 2 into, that is 100 into 2 to the power 100. So that let us subtract s minus 2s is negative s is equal to, so here 1 minus 0 1 plus 2 times 2 minus 1 times 2 will be getting, so 1 times of 2, and 3 times 2 square plus 2 times minus 2 times 2 square is 1 times 2 square, and here 4 times 2 cube minus 3 times 2 cube is 1 times 2 cube, and so on and continues. So 100 minus 99 will give it getting 1 times 2 power 99, and again here minus 100 times 2 to the power 100. So s is negative s is equal to, so this is 1, 2 plus 2 square plus 2 power 3 plus, and so on up to 2 to the power 99. So till here we can say this is the geometric progression with the 100 terms are there. So this is 2 power 0. So counted 100 terms minus 100 times 2 to the power 100. So sum 2 in terms in GP we can write Sn is equal to A into R to the power n minus 1 divided by R minus 1. So negative S is equal to, first term is 1, and R value is here, A is equal to 1 and R is equal to 2. So 1 into 2 to the power of 100 terms, the 2 power 100 minus 1 divided by 2 minus 1 minus 100 times 2 power 100. So we can write S is equal to, or negative S is equal to 2 power 100 minus 1 divided by 2 minus 1 is 1 minus 100 times 2 power 100, which implies S is equal to 100 times 2 power 100 minus a negative taken common, so 2 times of 100 plus 1. So 100 times 2 power 100 minus 1 times 2 power 100, 2 power 100 taken common. So we can add 100 minus 1 plus 1, that is 99 times 2 power 100 plus 1 is the answer. So which is our option B. Option B is the answer. Given omega is the complex cube root of unity, then we need to find omega plus omega power 2, omega to the power 1 by 2 plus 3 by 8 plus 9 by 32 and so on, 27 upon 128. Since omega is the complex cube root of unity, so we can write omega power 3 is equal to 1 and 1 plus omega square is equal to 0. So let us consider this series. Let S is equal to 1 by 2 plus 3 by 8 plus 9 by 32 plus 27 upon 128 plus and so on. So we can also write as 3 power 0 upon 2 plus 3 power 1 upon 2 power 3, 3 power 2 upon 2 to the power 5, 3 power 3 upon 2 to the power 7 and so on. Or we can also write S is equal to 1 upon 2 taken common. So 3 power 0, that is 1 plus, and here we can write 3 by 2 square, and here we can write 3 by 2 to the power 4, 3 square by 2 power 4. Next 3 power 3 divided by 2 to the power 6 and so on up to infinity. So which is equal to 1 upon 2 times, and here we can identify that this is the geometric progression with the first term is equal to 1 and common ratio is equal to 3 by 2 square. So that is 3 by 4. So sum to infinity in GP is equal to 1a upon 1 minus r, and here r is less than 1. So we can write a upon, that is 1 divided by 1 minus 3 by 4, which is equal to 1 by 2 into 4 upon 4 minus 3 is 1, which is equal to 2. So the given sum is 2. So therefore we can write omega plus omega to the power s, which is equal to omega plus omega to the power 2. Since we know that 1 plus omega square is 0, so omega plus omega square can be taken as negative 1. So minus 1 is the answer, which is our option A. The product of n positive numbers is unity, then their sum is. So let us consider, let x1 comma x2 comma x3 and so on xn are n positive numbers, and it is given that their product is unity, that is 1, x1 into x2 into x3 and so on up to xn, the product of these numbers which is equal to 1, and their sum we need to find out. Let us apply arithmetic mean is greater than or equals to geometric mean concept. That is, arithmetic mean of these n numbers as x1 plus x2 plus x3 and so on xn divided by n is greater than or equals to geometric mean, that is nth root of x1 into x2 into x3 and so on xn. So which is equal to nth root of, we know that the product of this n positive numbers is 1. So 1 to the power 1 by n, that is 1. So we can write x1 plus x2 plus x3 and so on up to xn upon n is greater than or equals to 1. So this can also be taken as x1 plus x2 plus and so on xn must be greater than or equals to n. So we can say that the sum of these n positive numbers must be greater than or equals to n. So it can never be less than n. So we can go with an option D. Given x is positive, we need to find the sum to infinity of the series 1 upon 1 plus 3x minus 1 minus 3x upon 1 plus 3x whole square and again plus 1 minus 3x whole square upon 1 plus 3x whole power 3 minus 1 minus 3x whole power 3 upon 1 plus 3x whole power 4 and so on up to infinity. So we can write, or let us consider, let 1 minus 3x upon 1 plus 3x is equal to r. So we can write 1 upon 1 plus 3x minus 1 upon 1 plus 3x into r plus 1 minus 3x or 1 minus, we can write it as 1 upon 1 plus 3x into r square minus 1 upon 1 plus 3x into r power 3 and so on up to infinity. We can see that this is a geometric infinite GP, infinite geometric progression with the first term a is equal to 1 upon 1 plus 3x, and the common ratio we can consider minus of 1 minus 3x upon 1 plus 3x. And since x is positive, so 1 minus 3x upon 1 plus 3x will be less than 1. So negative of, so we can say mod r is less than 1. So we can apply the formula sum to infinity is equal to a upon 1 minus r. So here we can add sum to infinity a, that is 1 upon 1 plus 3x divided by 1 minus of plus 1 minus 3x upon 1 plus 3x. So we can add 1 upon 1 plus 3x into 1 plus 3x upon 1 plus 3x plus 1 minus 3x. So we may cancel here 1 plus 3x and we can add 1 upon 3x and 3x gets cancelled, so 1 upon 2. So 1 upon 2 is the sum to infinity of the given series. So we can go with an option A. Given sum of first two n terms of the sequence 258 is equal to and so on is equal to sum of the first n terms of the sequence 57, 59 and 61. So let us consider S2n of the first sequence is equal to S dash n for the second sequence, and the first sequence with a common difference of 3. So we can write the first term a is equal to 2 and common difference d is equal to 3. So sum of first two terms, sum to n terms formula is n upon 2 into 2a plus n minus 1 into d. So we can write 2n upon 2 into 2 times of 2 plus 2n minus 1 into the common difference is 3. And coming to the second sequence 57, 59, 61 and so on. So here the first term a is equal to 57 and the common difference d is equal to 2, and sum to n terms we can write n upon 2 into 2a plus n minus 1 into d. So here we can write which is equal to n upon 2, 2 times of 57 plus n minus 1 into the common difference is, let us, is given 2. So let's simplify. So here we can write n times of 2 to the 4 plus 6n minus 3, which is equal to n upon 2 times of 57 2 times 114 plus 2n minus 2. So here we can n times of 6n plus 1 is equal to n upon 2 times of 2n plus 112, or n times of 6n plus 1 is equal to n times of n plus 56. So we can write n times of n plus 56 minus n times of 6n plus 1 is equal to 0, or n is taken common. N plus 56 minus 6n minus 1 is equal to 0. So we may write n times of minus 5n plus 55 is equal to 0, or n times of our minus taken common, or 5n taken common, we can take 5 common, minus 5n times of n minus 11 is equal to 0. So we can say either n is equal to 0 or n minus 11 is equal to 0, that is n is equal to 11. N cannot be 0, so n is equal to 11. So we can go with an option C. Between 1 and 31, there are m arithmetic means which are inserted, so that the ratio of 7th and m minus 1th m arithmetic mean is 5:9. We know that if there are m arithmetic means between a and b, so we have the common difference is b minus a upon m plus 1, and also the each arithmetic mean, the first arithmetic mean is a plus d, similarly the second arithmetic mean is a plus 2d, and so on. Some mth arithmetic mean is a plus md, and here given between 1 and 31, so let us write 1, a1, a2, a3, and so on am comma 31, so that these are m arithmetic means. So we can find the common difference, d is equal to b minus a, so a is equal to 1 and b is equal to 31, so b minus a, 31 minus 1 upon m plus 1, that is 30 upon m plus 1, and given 7th arithmetic mean upon m minus 1th arithmetic mean, the ratio is given as 5/9, 5:9. So we can add a plus 7d upon a plus m minus 1 of d is equal to 5/9, or we can simplify and write 9 times a plus 7 nines are 63, d is equal to 5 times a plus 5 times of m minus 1 of d. So on simplifying, we can write here 9a minus 5a plus 63d minus 5md plus 5d is equal to 0, or 9 minus 5, that is 4 times a, plus 63 plus 5, that is 68 times of d minus 5 times md is equal to 0, and we know a is equal to 1, so we can write 4 into 1 plus 68 times of, or 68 minus 5m times d value is 30 upon m plus 1, which is equal to 0. So on simplifying, we can write 4 times of m plus 1 and plus again here 30 times of 68. So we can write 68 3 times 2040 minus 150 m upon m plus 1, which is equal to 0. So we can write 4m plus 4 upon 2000 plus 2040 minus 150m is equal to 0, where m plus 1 cannot be equals to 0, that is m is not equals to minus 1. So 2044, and this is 4m, 4m minus, that is minus 146 m is equal to 0. So m is equal to 2044 upon 146. So we can write 1022 upon 73, and 73 we can write here 14 times. So m is equal to 14. So we can go with an option A. Given a sequence 1 with 1 time, 2 with 2 times, and 3 here 3 times, and 4 4 times, and 5 with 5 times, and so on it continues. Then what will be the 100th term? So here we can say 1 is obtained in the first position. The first position is 1, and 2 is obtained the beginning number. 2 is obtained in the second position, and 3 is obtained in the fourth position, and 4 is obtained in seventh position. Similarly, the next 5 is obtained in 11th position. This is 11th position, and if it continues, and this it continues, so what will be the 100th number in which position lies? So to find out that, let us make a sequence of the positions 1, 2, 4, 7, 11, and so on. So we can also write the first position as 1 plus 0, the second position is 1 plus 1, third is a fourth position is 1 plus 3, and next 1 plus 6, 1 plus 10, and so on. So we can also write 1 plus 0, 1 plus 1, 1 plus, here 3 we can write 1 plus 2, and here 6 we can write 1 plus 2 plus 3, and 10 we can write 1 plus 2 plus 3 plus 4, and it continues, so that we can generalize the nth term as 1 plus, it's a sum of n minus 1 natural numbers. So that is n minus 1 into n divided by 2, because we know that sum of first n natural numbers is n into n plus 1 by 2. Then summation of n minus 1 natural numbers can be taken as n minus 1 into n upon 2. So on simplifying, we can get 2 plus n square minus n divided by 2. So that is n square minus n plus 2 upon 2 is the position. Now to identify which number is existing in that, let us see. Let us consider in 14th position, means in second position here, if we substitute n is equal to 2, you will be getting 2 number. For n is equal to 1, you will be getting 1. For n is equal to 2, you will be getting 2. For n is equal to 3, sorry, for n is equal to 4, you will be getting number 3. Similarly, if n is equal to, for what number? Say if n is equal to 13, let us take 13 from among the options. Then we can say A13 is equal to, means the position, 13 square minus 13 plus 2 divided by 2, which is 169, minus 11 divided by 2, which is 150, 8 divided by 2, which is 279. So 7 in 13th position we can see the number 79. So 13th position we can see that there is a number 79. Now in 14th position, suppose if n is equal to 14, and here we can see that A14 is equal to 14 square minus 14 plus 2 upon 2, which is 196 minus 12 divided by 2, that is 184 divided by 2, which is 92. So we can see that in 14th position, so by the 14th position, we can observe the number is 92. And in 15th position, for n is equal to 15, we can see that 15 square, that is 225, minus 15 plus 2, that is minus 13 divided by 2, so which is a 212 divided by 2, which is 106. So and in 15th position we can see the number is 106. So we can say clearly that your 100th number is in 14th position. So in 15th position beginning number is 106, means 14th position 92 started, and 100 will be in between. So we can say 100 is in the 100th term. So the 100th term can be taken as a 14. So which is option C. Given nth term of a GP 128 and sum to n terms is given 255 and common ratio is 2, we need to find the first term. Let A be the first term and common ratio is R. Then we have nth term in GP is A into R power n minus 1, which is given 128, and sum to n terms is given Sn is equal to A into R power n minus 1 upon R minus 1, which is given 255. So we can write here A into R power n upon R is equal to 128, or A into R power n is equal to 128 times R. Let us substitute here A into R power n minus A upon R minus 1 is equal to 255. So we can write here 128 times R minus A upon R minus 1 is equal to 255. So from this both. So since R is equal to 2, so 128 into 2 minus A upon, so 2 minus 1 is equal to 255. So further we can write 256 minus A upon 1 is equal to 255. So A is equal to 256 minus 255. So A is equal to 1. So we can consider the first term is 1, which is option A. Geometric mean of some n numbers. If A1, A2, A3 and so on An are some n numbers, then the geometric mean can be given by Gm is equal to nth root of A1 into A2 into A3 into and so on An. So here we can write geometric mean of these numbers. We can take it as geometric mean is equal to nth root of 7 into 7 square into 7 power 3 into and so on up to 7 to the power n, which is equal to nth root of 7 to the power 1 plus 2 plus 3 plus and so on up to n. We know sum of n natural numbers, summation n is equal to n into n plus 1 divided by 2. So we can add 7 to the power 7 to the power n into n plus 1 upon 2 nth root, which is equal to 7 to the power n plus 1 upon 2 whole to the power 1 by n. So we can write 7 to the power n plus 1 by 2 is the answer, which is our option A. Sum to 20 terms of the series 1 into 3 square plus 2 into 5 square plus 3 into 7 square and so on, and its nth term can be 1, 2, 3 and so on n, and this is a 2n plus 1. We can say odd number square 3, 5, 7. So we can write 2n plus 1 whole square. So nth term, so that is Tn is equal to n into 2n plus 1 whole square. Therefore, the series can be given by summation of Tn, which is summation of n into 2n plus 1 whole square. On simplifying, we can write summation n times of 4n square plus 4n plus 1, or summation of 4n cube plus 4n square plus n. So which can be written as summation of 4n cube
plus summation of 4n square plus summation of n. And we know that 4 times summation of n cube, and here also 4 times summation of n square plus summation n. Summation of n cube is n square into n plus 1 whole square upon 4, and summation of n square is n into n plus 1 into 2n plus 1 upon 6, and summation n is n into n plus 1 upon 2. Now since we required sum to 20 terms, so this is Sn, and S20 can be taken as substituting in place of N20. So 4 into so here we can let us write here S20 is equal to 20 square into 20 plus 1 whole square, that is 21 square, and here it comes 2 upon 3 times 20 into 21 into 22 is a 40 plus 1 41 plus 20 into 21 divided by 2. Further simplifying, after calculation, you will get the sum to 20 terms is 1888090. So which is our option C. We need to find the sum of infinite terms of the geometric progression, which is given root 2 plus 1 upon root 2 minus 1, 1 upon 2 minus root 2, 1 upon 2, and so on. And here the first term a is equal to root 2 plus 1 upon root 2 minus 1, and the common ratio, let us take common ratio third term by the second term, which is 1 upon 2 divided by 1 upon 2 minus root 2, which is equal to 1 upon 2 into 2 minus root 2. Let us rationalize it. So we'll get 2 plus root 2 divided by 2 plus root 2. So which can be taken as 1 upon 2 into a plus b into a minus b, that is 2 square minus root 2 whole square is 2 divided by 2 plus root 2, that is 4 minus 2 is 2. So 2 upon 2 into 2 plus root 2. So we got 1 upon 2 plus root 2 is the common ratio, and sum to infinity in GP is a upon 1 minus r. So we can write a value is root 2 plus 1 upon root 2 minus 1, the whole divided by 1 minus r is 1 upon 2 plus root 2. Simplifying, root 2 plus 1 upon root 2 minus 1 into 2 plus root 2 upon here 2 plus root 2 minus 1. So which is root 2 plus 1 into, here we can take root 2 common. So we can write, because 2 is nothing but root 2 into root 2. So root 2 of plus 1 divided by, here 2 minus 1 is 1. So root 2 minus 1 into root 2 plus 1. So we can say root 2 into root 2 plus 1 whole square divided by the denominator a plus b whole square root 2 whole square minus 1 square. Root 2 whole square is 2, 2 minus 1 is 1. So we can write root 2 times root 2 plus 1 whole square divided by 1. So which is our option A. We need to find the eighth term of the series 2 root 2 and root 2 and 0 and so on. Let's find which progression it is. We can clearly observe that the difference between 2 root 2 and root 2 is root 2, and again 0 and root 2 is root 2. So we can say it's an arithmetic progression with the first term a is equal to 2 root 2, and the common difference between these two d is equal to root 2 minus 2 root 2, which is negative root 2, and again between these two terms 0 minus root 2 is minus root 2. So we can conclude that the common difference d is equal to negative root 2, and hence the eighth term a8 is equal to a plus 8 minus 1, that is 7 times d, that is 2 root 2 plus 7 times of minus root 2, which is 2 root 2 minus 7 root 2. We can take minus 5 times root 2. So which is our option A.